There we go. All right, so okay, right now what we've done so far is try to understand how a real survey works. But what you all have done, which was a wonderful little exercise, and I think it's totally worth the extra time it took, was to understand how you think about what's going on. Because when you're out in the field, you're thinking about what's happening biologically. Out here, we were thinking about what's happening psychologically, whether it's psychological damage or anything else. There was something happening, and those observations that you gave are incredibly valuable. This is exactly how a biologist thinks when she or he is out in the field, and that's very, very valuable and very useful for us to go into the next session, where we will try to talk about site and survey covariates. Okay, so to begin with, you might remember this image that we had used in one of the first presentations, where we try to understand what's occupancy. As you all know, it can be defined as the proportion of sites out of the entire study area which are occupied. So in this case, 53% of the total sampling units are occupied. Alternately, you can explain it as the probability with which each of these 15 grids will be occupied by the species of your interest. Both mean more or less the same thing. In reality, neither occupancy nor detection is ever uniform. In some cases it is, but in most cases it's not. Species distribution. Species love certain habitat, they don't like certain habitat. We just did a simple exercise with 8s and 9s, and in those 30 minutes we had some incredible observations about what affected detectability. Those who had smaller screen had fewer detections, those who had bigger screen had better detections. Just that much provides us an understanding that detection probabilities are not always constant or random. They're sometimes associated with a certain parameters. First, we'll quickly go through site covariates. Now, what is a site covariate? And these are the two terms we will see a lot throughout all the way till we complete the analysis and the interpretations. Site covariates are those variables that affect probability of a site being used or not. How do we look at it? Let's say our same example, which is where we have 8s in 9s. These are the same graphics. If you look carefully, it has the same grids and the same detections here as well. But let's say there is a habitat which is a green habitat. Now this green could be pasture, this green could be forest, and the white habitat is a gray habitat. Just call it anything like non-habitat. Now your study area is divided in these two types of habitats. It's very important to remember, you might recollect that we mentioned that there is a homogeneity assumed within the site of our interest. And in this case, what we need to look at is that each of these sites, each of these sites is treated as homogeneous, even though you see part of it is non-habitat here, and so on. How do you deal with this? One of the simplest ways of dealing with it would be to just put numbers. What we've done is we have estimated the proportion of that sampling unit as your conducive habitat or not. So if you see, these are all zeros, but these are all zeros over here. But look at this one, only 5% of it is habitat, is green habitat. 45% of it is green habitat, 94% is green habitat, and so on. So we can estimate probability, we can estimate the habitat value or a proportion value for each of these sampling units. And that's a fairly reasonable means to determine how habitat might affect the probability of 8s living in the study area. What it basically means that instead of like this, your data will look like this, because you have to have a uniform value for each of these grid cells. So we will have a single value for this entire cell B2. We will have a single value for A1, single value for D1 and E, and so on. Now remember, this is why it is also very important to have the right size. If you have very big grids, then you might be merging, or you might be mixing up a lot of variation that's there, and lose out on some valuable information, or you might completely miss some of those patterns that might be there. So if this is too big for you, you might as well have smaller grids. Have smaller grids, and then this one and this one and this one and so on. You might as well do that by going back to the back to this one, and then you re-estimate these values. But as long as we are considering this to be a reasonable size, this is how we will reduce the resolution of information that we have to match our occupancy sampling units. The other way of dealing it with is simply just divide it into green habitat and gray habitat. Here what we have done is those habitats which had very little green, we've just simply ignored them. We just call them they're white. If they, let's say you decided a threshold of 50%, less than 50% non-habitat, more than 50% habitat. Now we are calling it a categorical variable. A unit, a sampling unit, one of the sites is either green or it is white. There's nothing in between. So this becomes a categorical covariate where it can either have a value of 1 or have a value of 0. Now, some of you who were part of the first training might remember that there was this little exercise we did where we created a scenario where there is a river and there are animals distributed as a function of distance from the water. Animals love water, so there were more animals closer to water, fewer animals away from water. We did a bit of a counting there, and we counted that different grids had different number of animals, but there seemed to be some sort of a pattern here. Now, if you look at here, what we did was we simply created a function, a relationship between distance. Oops, sorry, what am I showing here? Yeah, we created a relationship between distance and count. So you see, as the distance from water increases, the count overall seems to decrease. So we have units which were further away from water had fewer and fewer animals in them. So we decided, okay, that's a relationship, and then we created a what we call as a model. And model is nothing but a in this case we use a simple generalized linear model, which is nothing but a straight line equation. What we did was we tried to predict count based on the distance. And when we run a simple regression analysis, it gives us this equation. What we can then do is, using this equation, we can what we can do is we can predict. Now, if I did not know, if I had not surveyed cell E, and I know the location of cell E, which is 2.7, maybe somewhere here, and then I can predict how much the count should be. So it will give me a count of, let's say, in this case, what was it? I think it gives 3 point something, whatever. It's as close. This is the real number, and it gives us a value which is as close as possible. In other words, if we have a regression analysis, a regression equation, and you know one of the variables, you can predict the other variable. It's a fairly straightforward thing. Now, problem with this kind of a model is, can anybody think what's the problem here? What will happen if my distance is 10? If my distance is 10, and please feel free to put those comments in the chat, but if my distance is 10, look what will happen. I'm going to go, I think there is a slide here. If I do a distance 10, it is going to tell me a negative count. Now, can animals exist in negative populations? I don't think so, right? You can either have 0 animals or you can have millions of animals. You cannot have -3 snow leopards in an area, or you cannot have -8 ibex in another area. There'll either be 0 or there'll be a value above it. So one of the basic premises of wildlife populations is that they're always more than 0, right? They always have to be more than 0. There can't be negative populations of species. How do we deal with that? A very simple solution. We change the relationship and we go on logit scale. The same equation, if you create it on the by logit scale here, we can just do it on exponential. If you convert count as exponential count, you will see that for whatever distance you go further, it will never ever come to 0. It will never go less than 0. It will just, the minimum for whatever value of distance, it will stay at 0. So it solves a problem. It basically provides us with a model which predicts or which restricts our data from 0 to infinity. Yes, this the curve is very strong, so we have to be careful how the model performs. But apart from that, it's a fairly good solution for us. And in this case, it does a good job. So now we can use the model to predict what will happen if I have 10. Then it still says, I think it was still doing it. Right? What happened? Yeah. So it was predicting for 10. It gives me an estimate of, yeah, there it is. So it's somewhere 0. It's not going to go less than 0. So that problem is solved. We don't have a scenario where we might end up with -5 animals at a certain distance. Now, the key here is, with occupancy, there's another problem. Yes, we can use a straight line, but then it will be from -infinity to +infinity. And occupancy, because it's probability, it cannot be less than 0. And at the same time, it cannot be more than 1. So it's restricted. You can either have an occupancy of 1, which is 100% probability of a species living in a certain area or using a particular landscape, or they can be 0 probability of using. You can't have minus probability of using a species. You cannot have more than 1 probability of using a particular habitat, which is where we have another function, a mathematical function, which is called logistic regression. It looks scary, but trust me, it's a very simple thing. All we are doing is we're just taking the straight line equation and putting it twice. And here is a simple, we are just dividing the exponential of that value by 1 plus exponential of that value. That's the only difference there is between a straight line equation and a logistic equation. I'll send you a simple Excel sheet. Just plot it and you will see for a value of -infinity to +infinity, the probability of occupancy, whatever values you put in this equation, they will always range between 0 and 1. And to show you, I think the next slide should do that. Yeah, there we go. So all I did was I just, again, this is a hypothetical situation, but what we are saying is that my 8s like green habitat. So there is more probability of them using those habitat patches which are completely green, and less probability of using those habitats that are more that have less green. And there is a function, and you will see that this is the logistic regression function here. You will get a value of beta 0 and beta 1 from occupancy analysis, and then you plug in any value of habitat and it will make it somewhere between 0 and 1. In case of the categorical variable, where we have a value of 0 and 1 only, there's nothing in between, you will have something like this. You will, for a gray habitat, it's not 0 because there were still some animals using the poor habitat, or there's some probability with which the 8s are using those grid cells which are gray in color. So it's, let's say, 0.23 or whatever, but there is a very high probability that they're going to use the grids which are green. So for gray habitat, they have less probability. For green habitat, there is a greater probability. Now, moving to the next one, same principles, literally the same principles apply with the detection probability. Here again, detection probability and those covariates that define the probability of detecting a species given presence are what we collect in case of detection probability. I won't go through this again. I know we've had enough, but they're basically showing the same thing. What affects our ability to detect a species if present? Now here, what you guys have already done, and this is why I thought it was a great idea to do that little discussion earlier. You guys have come up with time, which is effort, skills, which is equipment, climate, in this case, internet connectivity, and others. So these are exactly the covariates that I had thought could be affecting it when Justine and I were putting it together, and you guys have already put it there. Now that's where it helps to be able to invest some time and resources in understanding or in observing and making those observations to make these predictions. And it's a very important exercise for you to be able to create the right sets of models for your analysis. The only key point we need to remember here is that while a sampling unit has to have a constant value for its entire length and breadth, a detection covariate can vary within a sampling unit. What it means is that imagine if first observers got 10 seconds, second observer got 5 seconds, and so on. You are giving different times to different observers. That's a perfectly doable and a practical and a pragmatic situation. What else? We've just discussed different screens, that become a survey covariate. Different type of internet connectivity, that becomes a survey covariate. So anything that is affecting your ability to detect the presence of 8 in a habitat is, if you can put a finger on it, that this is what's affecting it, that becomes the covariate for you to be able to make use of. And I think we're just close to the end of this one. Let me delete this. And then just a recap, for a single season distribution survey, there are two things that you're estimating: probability that a site is being occupied or used, and this probability is affected by site covariates that remain constant for my survey period. They don't change during that within that duration. They remain constant, and they are homogeneous, or they're assumed to be homogeneous for defining that entire sampling unit. They are flexible in a site. I mean, the site occupancy surveys are flexible, that you don't need to survey every nook and corner. You can sample them using representative random sampling, or if you have the resources, do all of it. Like in this case, Justine really got tired, and she made sure that we didn't go through all of it, and it's fine. If we were only sampling left to right, then it was a problem. But because we had randomly aligned grids, we will see tomorrow, we will see in the next session which grids we could not sample. And if they're just randomly located, it's not a problem. We will be able to predict what the probability of occupancy of 8s within those was. But the second element, probability of a species of interest being detected, it does get affected by survey covariates, which you guys have just looked through. So anything that affects your ability to detect an 8 in a habitat is a survey covariate. Anything that affects an 8's probability to live in a certain area is a site covariate. So in other words, if 8 is a species, it loves green habitat, that is a site covariate. Detection covariate has almost nothing to do with 8, right? Only in certain scenarios, and Abhishek will be talking about it, and we'll talk more about it later. But when you're looking at certain signs and where you're looking at signs, that's when it comes into play. But otherwise, the important point here is also that if you were tired, you just need to do the survey. You could have just waited and sat there. All you're doing is you're leaving a blank as an NA. We were saying you didn't survey it, no problem. We can still use that data as a valuable data. So Nawaz, as you mentioned, yes, you have to report to your boss, but as valuable as zeros are, NAs are equally valuable, because if you report a false 0 or if you report a false 1, then you're corrupting the data and it becomes very difficult to clean up. And that's why I think you cannot overemphasize the value of being honest and complete with your being honest. I think that's a key part. Being very honest about the survey, I think that becomes very important. So tomorrow when next class when we come back, we'll see how the distribution was. But this is how actually the species is distributed. The orange ones are where the actual 8s are, and the habitat is there. So you will notice there are some green habitats where the species is absent, and some white habitats where the species is present. So both of these, there are kind of overtures in both sides, and we'll look at it how well it is able to detect those. With that, I'd like to stop here. I know I've gone a little too fast, but that's in the benefit of time. And if there are any questions, we'll be more than happy to answer them.